Hello, everybody. Today we went to Snake Was Right's room and found Nathan, who is a very new flat earther there. He's very young and he's a really nice guy. I really like Nathan. But this day, me and a few of the community were trying to explain gravity to him, including Snake Was Right and Leo Filius and the amazing Dr. Chris Thompson, um, with sort of marginal success. And um, in trying to explain gravity to him and why things are falling downwards, I think it's important to use the language that people are using. So you'll see me all throughout this refer to sort of his terminology for what he's doing, so what is happening. I'm referring to his terminology. I think that's because the way we learn stuff is we learn it by connecting things that we know already with things that we don't know. So I hope you enjoy, and this is sort of trying to teach Nathan about gravity before he sort of I see him being sort of sucked into the flat earth movement and things like that. So hopefully we can sort of convince him that the earth's not flat and gravity is a thing. But this is sort of the process we go through, and sort of the Socratic method that we go through. So I thought it was kind of interesting, and of course the full room with everybody in it is up on Snake Was Right's channel, which I will link below. Hope you enjoy.
Lower than like kinetic energy. If
Why?
you
I'm
look
going to
at an
keep
energy
asking you
diagram, you
why.
have to have an activation energy to get something to change in chemistry. You uh, it takes more energy to be at a higher energy level. And so
Why?
rest is a lower energy
I'm
level,
going to
and that's
keep.
where
Sorry, Nathan. No, you're not explaining it, right? You're
it's
just saying
entropy.
there is this force gravity, and you need another force in order to overcome that force. I'm asking you
It-
why it goes down, right? What is the cause of that downward motion? And now, yes, saying you need a force to get it to go upwards, that's fine, right? That's what we think because there's it's overcoming the force of gravity. That's what the scientific explanation is, right? Unless
okay,
you
if
say, yeah, gravity exists, then you're not giving an explanation by trying to tell us that there is a force to overcome. I'm
Y-
asking you
You're
what that force is and how that force works.
you seem to be saying that it goes down because it falls down. So we're asking like if an object stays at rest, if I put a brick up against a wall and it's at rest and I let go, what is moving it down?
so if I'm holding this here to get it to go up to here, I have to put more energy in, and now there's
Right,
more energy required to hold this up. So
right.
now if I let this go, there if you were to just draw a band straight out from both sides, same density on both sides. Now below this you have denser air, and above it you have or
But
less dense
but if I
air.
move it left, it doesn't move back right.
Well,
I have a quick
it's
question.
equilibrium air on both sides.
Well,
Density.
okay. So I just this is the example that I'm using. So
Okay.
conservation of momentum sort of says that this, if I was to lift this right and place it here, I'm using sort of force to lift it and overcome whatever's pulling it down. Right? We agree that that happens. You have to use force to get it up to this height. Now,
Mhm.
if I let it go, conservation of sort of energy says that it should stay there unless another force acts upon it. So what is that force?
Oh no.
So you are going to you're going to lift it up. If you have it on your table, that's where it wants to be. Now, if
Why
you
does it
lift
want
it
to
up,
be
you're
there?
because that's where it's supported. It's
Can I ask
using its
just a quick
potential energy on
clarifying
the table.
question?
Go ahead, Leah.
Um, Nathan, are you talking about the concept of buoyancy?
Buoyancy would be an explanation. I know that people will say buoyancy
Because
uses
well, the reason I
gravity.
asked that is you know that the equation for buoyancy contains the gravitational constant, right?
Yeah,
Buoyancy only exists in a gravitational field.
and I would say you could call what you call gravity could be called like an accelerate. You could give it any other name, We
Mhm.
just
Sure.
call it
Well,
gravity.
the force of gravity is equivalent to acceleration out of a gravity, or just acceleration of the same force. Yes, but gravity isn't the same thing as acceleration. That's not how general relativity works.
No, it would be gravity is um
Technically, gravity is not even actually a force.
Well, yes, that's correct.
what that variable of g, you could
It's not a
put,
variable, it's constant.
yeah, you could put it in as the symbol of g, I guess is what I meant to say. You could put that as, call it a, or give it another symbol that is not g.
Yeah, you
Um,
could give it a different symbol. It still represents the same thing. Earth's gravitational constant. The gravitational constant of Earth's field. Gravitational field.
the constant of like you're talking the 9.8 meters per second, right?
Well, that relates to it. I believe that's derivable from it.
Yeah, that would be how that odd. I'm trying to think of the wording. Um, that is the average acceleration for an object. It's an agreed upon average, but that valuable that variable is the same. It's measured, so it would be the same on either model, and so you can use the buoyancy equation the same, because it's not claiming to be 10.7 meters per second per second. It's the same measured variable. It's just the word that you would give it for the buoyancy equation.
So you're saying that
So
your model can
Go ahead, Leo. Go finish up. I don't mean
go
to
ahead,
interrupt.
Leo.
so you're saying that your model can accommodate this thing. That's what you're saying. That seems to me what you're saying.
The 9.8, yeah, that's yeah.
So
That's
my
measured.
question is, do you think that mere accommodation alone is important, or do you think that actually predicting things is the important part when it comes to science?
That's what I was gonna ask.
Predicting is an important part of science. Yes.
Because modern physics would be capable of predicting these things, whereas it seems that your model can only merely accommodate them. So my question then would be, why wouldn't you favor modern physics over the model you currently hold?
Well, these values are measured on the Earth, but I like, with gravity being able to predict, if I gave you like the three body problem is infamous for gravity for not being able to handle three bodies.
Newtonian gravity.
By
Yeah.
the way, if anyone has not yet read the Three Body Problem series of books, do so now. Back to
Yeah.
the topic.
Okay.
I just want to check if you've seen stuff like if we take air out of the equation, right? We make a vacuum chamber, pump every little bit of air like it's a near total vacuum, and we drop a bowling ball and a feather at the same time. Do you know which one hits the ground first?
There, it's supposed to be the same time, but
Have you
there can be.
seen
Was it?
anything to confirm that? Like I can show you a video of them doing it.
Well, yeah, I know, like I've seen the thing with Brian Cox at NASA,
Right,
and I
right.
think it was a bowling ball and a feather.
Mhm.
There's some odd stuff about that footage, like them not showing a long drop, like one cut, one frame, because there are people who have also made videos of vacuum chambers, and some of them are tilted for whatever reason, but like depending on like the shape of the object, it might fall faster. Certain objects can. So like I think someone
It
got feathers
doesn't.
to be under a hammer.
It doesn't.
So
Yeah.
The whole point is with the gravitational forces is that the force needed to pull it down, to make it change its location, is exactly opposite to the force required to pull that amount of weight down. Sorry, it's opposite to the amount of force that gravity exerts on more mass. So those two things counter each other out. It means that without air resistance, everything falls at exactly the same rate.
Yeah. The Earth is technically pulling on, well, quote unquote pulling. The Earth doesn't really pull anything, but just speaking simplistically, the Earth is pulling on the moon with the same amount of force that it's pulling on the International Space Station. So,
Right.
Mm-hmm. So that measured value would be like it's what's measured. It would basically be how do you explain it? Like it's not a denial of the measured value of what we get, and how things work in a vacuum is kind of another thing, because they're like vacuum measurements are a bit different from Earth measurements. But like as far as why something would fall, the way that I mean, because I'm trying to think of how to word it to get back to Simos, is you have an object, and if you let it go, the air underneath it cannot support it. And so like if I drop it and it falls 1 inch, and now this new band of air underneath it cannot support it, it's going to keep going until it hits solid matter, because solid matter has an energy level that can hold it up.
Sure.
And
But
so
we
like
went
the
through that though.
explanation
We went through that, and we discovered that the sides of the pool also are solid matter, and that's not explaining why it falls downwards.
well, the
Now,
atmosphere is
let
also
me
solid
let
matter.
me just say this as well. I really liked what Mark said, right? I thought that was actually the killer point. So thank you, Mark, as always. When you pick up your pad, your iPad or whatever it is, what force are you overcoming to pick it up? Because you have to apply force to pick it up, don't you?
Yeah.
So what force are you overcoming to pick it up?
It would be the resting energy of the object.
Okay, and why does it have resting energy?
Uh, because
Wait, but that's the wrong answer.
It may well be, Leo, but I'm only going down his train of thought here. I'm not going down my train of thought.
Oh, I'm sorry.
yeah, it's why does an object have resting energy? It's at rest.
Yeah. Okay. So what gives it energy when it's at rest?
Its existence. Why does something have
Well, do you think
resting
it's
I
still,
energy?
in
think
other words, when it's on the table, do you think it's still trying to fall downwards, but something is stopping it?
Yeah,
What?
the
Why is it
table
trying?
is stopping
What?
it.
Okay. And why is it
No,
trying
no,
to
no.
fall
What's trying?
downwards?
I'm sorry.
Why is it trying to fall downwards when it's on the table?
It wants to be at rest.
Sure.
so.
That's
Let's
the same
look at it
answer you're
another way.
given.
I got a slight clarification. Do you think my ball and a bowling ball has the same resting energy?
Is the same resting energy. Um, they're gonna have resting energy. Probably the energy requirement for resting energy will probably be different.
Okay, so a
Uh,
bowling
like
ball.
it doesn't take it to, you can overcome the resting energy easier with that ball than a bowling ball. So they would
Right.
have different resting energies.
So what causes this ball to have less resting energy and the bowling ball to have more resting energy?
The mass, the density.
Right, the mass. No, it's the mass, because if I've got a huge ball exactly the same as this that's large, right, it'll be harder to overcome that resting energy, right?
If it was the same like weight.
Well, if it's the same
Yeah.
density, just say that it's
If they
exactly
were
the
the
same
same weight,
material
if
as
they were the
this.
same weight, yeah.
No. Exactly the same material as this. So this has got a certain density, right? This is a squishy ball, right? It's actually a juggling ball for those people that don't know. So you can squish it. Just say it's exactly the same density, exactly the same material, and it's just really big. Will this one still be easier to lift than the other one?
Theoretically, just to in terms of gripping it, yeah. And if you had like the same, if they're the exact same total density, like assuming if you had a bigger ball, it would get thinner material just to balance out the volume.
No, just say
If it
the
was
proportions are exactly the same. It's an identical copy of this. Just I've used an enlarged ray on it. And it's just a lot bigger, right? It's just a bigger ball. This one will still be easier to lift because there's less weight, right? There's less weight, right? It's
Yeah.
going to be lighter,
Yes.
right? So what it can't be the density that's causing this one to be lighter then, because the density of this, how dense it is the same as the large ball, right?
Yes. So
So
yeah, so mass. The mass would
mass,
be the difference. Mass and
right?
volume.
So the more mass something has, the more resting energy it has, right?
Mm-hmm.
That's gravity.
More specifically, that resting energy is generally referred to as gravitational potential energy.
Don't confuse
Yeah, potential
Leo.
energy is that's potential energy is another word for resting energy. Objects go between potential and kinetic
Well,
energy.
not
Right.
And we'll
necessarily. Objects in
So
motion
to
can
get
have
back to Mark's
potential
first
energy.
question, why does it take, right? What is the force you're overcoming to pick up the ball? You have to apply a force. And you said,
Yes.
well, it's this resting energy, right?
You're
Now we've
using
decided that the greater the mass, the more, in quote unquote, resting energy it
Energy.
has. And so the more force you have to put in to overcome that initial inertia, right? So what we're saying is, why, when something is sitting on the ground, even right on the earth itself, okay, and it can't go down anymore, it still has this potential energy, right?
This resting
Mhm.
energy. Yeah.
This
Yeah.
this resting mass, it still has
Yep.
the same mass. Okay, so what is it that's causing that resting mass?
It would be the
And
mass of the object.
Right. Right.
right,
And the more mass it has, the greater the force it exerts on the ground, right? Like, so if an elephant steps on a pallet or something, or a pad, it might crush it, where we don't. So the
Mhm.
more mass there is, the more downwards energy there is, right?
Yes, but it also does depend on the medium that the object is in. If you take that
Sure.
juggling ball and you have it in a fluid that is the
Hmm.
same density as the juggling ball, it'll actually be at equilibrium, and then you can move it side to side, up and down. You can fix it in an
Yep.
orientation, and it
But
will
that
But
goes
stay
back to
there.
that's
buoyancy. And
no, no,
again,
no. Hold on,
buoyancy
hold on,
has
hold
the
on, hold on, hold on,
gravitational
hold on, hold on,
constant.
hold it, hold it, hold it, hold
That
it.
doesn't.
But
Well, yeah,
that
that's
is
fine. I just want
true.
to point
No,
out
no,
that
no,
it's
no,
not
no, 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 no,
returning the
no, 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 no,
problem.
no, 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 no. That is true of the big ball as well, isn't it?
Mm-hmm.
Yep.
yeah.
Yes.
So that's go, Leo. Now go. Now buoyancy, Leo.
Yeah, no, I was just pointing out that it doesn't matter if you put it in a medium because we're just dealing with buoyancy, and you don't have buoyancy without gravity, so it doesn't overcome the problem. It's just
Well,
moving
there's a
it down enough.
medium regardless of what, if you're in a medium of juggling ball density
Okay.
or a medium of air, there's
It's
still a
also
medium.
it's also probably worth pointing out that these forces exist. These objects would behave the same if there were no medium. They would all attract each other the same way.
Well, no medium is still kind of a medium. Like if you're in a
Well,
vacuum,
no,
you're in a
Not
no
really.
density medium.
Vacuum isn't
I
really a
don't
medium.
really know what that means.
But the whole
There's still
point is that
space.
when say the liquid is heavier, it's heavier, it's more dense than the ball, right? The ball will go up, and that's because the more massive something is, the more it gets pulled down, and so it basically, that medium then pushes the ball up, because it will basically hit the bottom, compress, and then it will start to push it up. That's why when you swim down in the ocean, it gets more and more pressure on you. It's because everything's being compressed. And so the
The
further
density of the
away,
ocean water changes.
yeah, that's how the ocean water changes. So when it goes up, it's basically that pressure's being relieved as it gets to go up. But this ball, if you release it underneath the water, it will probably float up until it finds the density that it's at.
Mhm.
And all of that is actually gravity. That's all gravity doing it.
Well, and or it's buoyancy. I know gravity is in there, is in that equation. But if you if you let a balloon go, it's going to go up until it hits that medium where it's at equilibrium with the helium in it, with the surrounding medium. Density towers, like people will make like dish soap,
Mhm.
honey, water, and then they put all these objects in there and they go to their density level.
Yeah.
That is a relationship of the density of the object compared to the density of the medium that it's in, whatever
Yeah,
kind of fluid that it's
In a
in.
gravitational field,
yeah,
yes.
Yeah.
that's only true
None
of
of this would be
these.
happening in a vacuum.
Yeah, it's also only
Yeah.
true in
Their
particular
parabolic flights
types
can
of.
mess up
Hang
density
on, hang
towers
on.
too.
It's also true in particular types of medium, right? So if you have something like a metal ball, right, it will quite happily rest on wood. Now, wood is a lot less dense than the metal ball. So, according to your last statement of theory, you would expect the metal ball to fall through the wood, but obviously it doesn't.
So like if you take that metal ball and say you have like a thin piece of plywood or something,
Yeah,
you take that heavy metal ball and set it on there.
yeah.
The energy of the ball itself and the weight from you gently setting it on there is not going to be enough to break the wood. But if you
Yeah, why?
I don't throw very hard,
Why
but
though?
if you
Why
take
though?
a
Because
pitcher who
hang
can
on, hang
actually
on.
throw the ball,
I'm asking you why that's the case. Because you just said these things find their density, right? Well, that's not the case in solid materials, is it?
yeah, so that ball has an energy that it puts into the wood, and the wood is able to match that energy so that it doesn't
Correct.
break the wood. But if you take that same metal ball and you throw it, you're going to have more energy in that ball. So by the time it hits the wood,
Right.
it's going to actually break through the wood
Good,
if
good.
that wood can't sustain that energy.
Okay, so that's not to do with density though, is it?
Well, that's it. That's like the flat Earth would explain it using density, using energy.
Yeah,
These
but it's not to do
variables.
with density because we've just said if you put the metal ball on wood, it doesn't fall through. The wood
Mhm.
is, even though it's considerably less dense, is going
Solids
to
have a very
support.
high energy level compared to fluids.
Right. Okay. So it's not to do with density when it comes to solids.
Wait, but that's not
Well,
actually always true. It takes more energy to turn a solid like iron into a liquid than it does for it to be a solid. So iron as a liquid would have more energy. That's why iron as a liquid glows. And this is coming from somebody who's worked in an iron foundry in the melt department.
Really?
it's the
Same's true for ice.
connectivity of the molecules. Solid iron is more, the molecules are more connected than in
Okay.
the liquid.
So what
Okay.
with regards to the wood though, you understand it's not about density at that point. It's about how much energy you can put into the material
Yeah,
itself.
because you can't move an object through solids.
Static repulsion.
Yeah.
So I have a
Okay.
question. If
And
you say
So
things
it's not
fall,
about density. Let me finish up because I'm
Okay.
out of here. Right. So my
Okay.
point being is every time you've gone to this density argument, right? Firstly, it was in the air, then it was in a swimming pool. Now we've got it on. Now we've got metal on wood, right? Every single time we've gone there, density is not going to be the answer. With Mark's idea about energy and mass, right? We've already agreed it's to do with mass. It's not to do with density. So every time you mention density to me, I'm going, well, you're not understanding what we're talking about because it's not about density.
Well, density does have to do with where an object finds rest.
Can I?
Yeah, that's
Well,
buoyancy. But I want to revisit your idea of the
okay.
air.
Let me say goodbye before you do. Okay. Look, thank you very much, Nathan. I really appreciate that. Thank you for answering the questions as honestly as you can. I really appreciate that. And yeah,
Absolutely.
we unfortunately we didn't get to clear up the philosophical side of science and creation.
Oh,
But
I would love to talk about
I
that. I can
think,
pick that up later, Simus.
oh, if you can, Leo, that would be great. I think you did agree with me in broad terms that science had a philosophical grounding, and
Mhm.
also creation has a science grounding as well. Not creation, not creator, but creation, right? The big difference
Yeah.
between the
Okay.
two. So I just want to say thank you so much for saying that outright. I really appreciate the honesty there. And I'll leave you with one last thing, which is to say there's a lovely experiment that I've seen. If you get a large book, okay, you put a feather on top of it, all right, and then you drop them both to the floor, you'll see that the feather drops at the same rate as the book. The reason being, of course, that there's no wind resistance on the feather,
No
and
air
both
resistance.
gravity
Yeah.
is acting on both of them. So
It drags behind the book,
it's doesn't
No,
drag.
it doesn't.
It just falls. It just
Yeah.
falls.
or
Right.
was it
And
draft?
no, there's no draft. It's just literally falling. And it's a good experiment you can do by yourself repeatedly, and try and explain it, or try and get to the idea of density, trying to explain what's going on, because they're clearly different densities, and clearly you'd expect them to fall at different rates if your idea of density was correct. But anyway, thank you so much. I really appreciate it. Thank you, everybody. Thank you, Snake.
Thanks,
And
Simos.
I'll see
Good
you all
seeing you,
another time.
Simus.
Take care.
Can I
See ya.
just wanted to play off of what Simus
Okay,
said really
Simus.
quickly, just because I think it's interesting, is that humans have actually known for like thousands of years that much, much denser and heavier objects, like if I took a 36-pound cannonball and then like a 4-pound book and I dropped them like 900 years ago, I'm going to see them fall at the same rate. And this was actually recorded by some people in various places in history as being something that was interesting, because humans' intuition would have told them that something heavier should fall faster. It should hit the ground first, but it doesn't. It hits the ground at the same time as the book. And there is actually a much more fundamental question that I do want to ask you, Nathan. What do you think relates the mass of an object? So I think we both would agree, just to lay some ground here first, I think we both would agree that objects of different masses, if we, we're on Earth, we're on the ground, we're like, say, in a Walmart parking lot, we got a big scale. Doesn't matter the size of the object, doesn't matter what kind of object it is. It could be something weird, like, say, the Walmart store that we're in the parking lot of. How much does it weigh? We can put it on this scale. So it's a magic scale. We can weigh whatever we want.
Okay.
I think we both would agree that things with more mass are going to weigh more on that scale, right?
Mm-hmm.
So what do you think relates the mass of an object to the increased force it exerts on the surface of the Earth, or in this instance, the scale? Why do you think that it is? Here, let me turn my camera on, because I want to make clear that, so I have autism, so if I sound like I'm being rude, because sometimes I just like
You're
say
good, man.
things in sort of a blunt way, because I don't want to come off as like insulting you or anything.
Oh,
I'm
dude, I love this
genuinely interested in a
conversation.
discussion. But I am curious, what do you think it is relates the mass of the object to the amount of force that it pushes down on the scale with, such that
resting
more mass
energy.
means more force pushing down? Yeah, if we just call that resting energy, why does
Right,
more
right.
mass mean more resting energy?
Because it would be like, if you wanted to move that object, you would have to put more force into it to get it to go into kinetic energy. So because of its mass,
Inertia.
it would be, yes, you would have to, it's basically, the resting energy is also kind of another way of what do you have to do to get it into kinetic energy.
Mhm.
So it would be, if you have more mass, it's going to take more effort. You have to put more work in to move that object. So that would be I think the relationship between mass and energy, resting energy, potential energy, and that type of thing, like that. I
So
think that's
then how
the
come?
relation.
So then how come two different objects of two completely different masses would fall toward the Earth at the same rate, barring air resistance?
Can I? Okay. So do you know what? Because I'm not familiar. What is like the longest distance that we've dropped objects that are, maybe, because like you said, a book and a ball, they would have different air resistance. And so what have we dropped these things from? And I guess it would be like, we don't have planes that fly over a vacuum tube that reaches up to them to be able to determine this. But like, what, maybe like, I just am curious, the distance, in a greater distance, might an object be able to gain more speed, more velocity?
Well, when falling toward the Earth, an object is going to gain a velocity up until it reaches the
Free fall.
medium, a happy medium between the gravitational force of the Earth and the air resistance of Earth's atmosphere. If you just took away Earth's atmosphere, then we could just ignore that perturbative factor. But the object that we've dropped from the highest height, I'm pretty sure, wasn't that the guy who jumped from like 25 or 30 miles high? Or the
Red
guy
Bull
The
jump?
Red Bull.
jumped? Yeah, the guy that jumped from like almost the edge of space.
Yeah, the Red
Bumgarner?
Bull jump. Baumgartner, yeah.
Yeah, well, isn't he the object that like humans? I don't know if
But
he
there
could
would be
really
I
air
say
think-
resistance there,
created.
right?
I think what he's asking is that comparative drop that we've done between, say, I think it wasn't it the Aristotle experiment where he dropped two balls? I'm thinking of the wrong person, aren't I?
I think they've done stuff off like the Leaning Tower of Pisa as well, like dropping. But there's
Right.
air resistance there.
Well, but what the
Sure.
point that I wanted to get at with bringing that guy up is that there was a lot of stuff that they had to a lot of potential problems they had to be able to preempt. There was a lot of preparation for what they did, and they had to factor in the gravitational constant and the gravitational force of the Earth. And with respect to the calculations that they had to do to ensure this man's safety when he made the jump, everything went exactly according to plan, almost as if they were working from solid math and solid physics when they were doing their calculations. Why is that? I mean, assuming that's all wrong, why?
No. And I think that's actually a misconception about the flat Earth. A lot of math, a lot of these things that physicists are doing, accurate, absolutely no disagreement. The interpretation of why we have this 9.8 or anything like that, those are all more on the why is a philosophical. It's what it is, what it does in reality is not a dispute at all. Like the math that these people are doing is accurate. They're going to say, okay, he's going to fall, he's going to have this sort of drag coefficient, his resistance in the air, this is how he'll fall and this is where he'll be. Like that is all like those, there's no in on it with that kind of stuff. Like these mathematicians are very smart people. You're very smart, very accurate with these. Math is very precise. It's very, for a lot of people, it's very challenging. And like I know I'm gonna have to study a lot when I'm going through these physics classes. I'm gonna have to do a lot of problem solving and work through this stuff because it is difficult. But these
how
things
come-
are accurate, and I like that is not a dispute of flat earthers. These mathematicians know their equations, the why, the philosophical, that like Simon said, like.
But if those equations are correct, then the Earth would be round.
Yeah, how
Well,
come we have
If
to
general
account
relativity is
for-
correct, it can't be the case that the Earth isn't spheroidal.
An object going down is an object going down. Both models claim that Felix is going to fall to the earth.
But how come we have to account for a downward acceleration and we can't solve these equations just with density and buoyancy?
So I think we have these equations solved because that was the mind frame of our academic system, and so the academics got there first through a gravitational mindset, but a measured variable. If you have a stopwatch and drop something in a vacuum, like like that's going to be a measured variable. What you ascribe to why it falls is going to be on a philosophical side, but they got there first using the model of gravity, and so that's what it gets
But
attributed to.
it is something's accelerating objects towards the ground. So it seems like you're saying that if we lift something up, it has to. It's like has a negative or a energy deficit and must come back down. Is that right?
Yeah, so like that where if you lift something up, it's not going to be able to, that air, if you let it go, doesn't have the energy level to keep it at equilibrium. There's a difference in the energy levels. So it needs to go, if it's at
Is
this
it
level
because-
and it's going either direction, it's the same, it's going to run into the same problem. This energy band is not enough to support me anywhere on this elevation. So I need
Is
to
it
go
because
up
it
or down.
started? Is it because it started down? It has to go back there, or are
Yeah,
you
just
just
like if
saying-
you had a beach ball and you put it down to the bottom of a pool, it's going to go up.
So
Yeah,
why
it,
do
it has a
is there
preferred
are there
direction.
any? If I dug under the ground, I never lifted the rock, but if I dug under the rock, is it just going to float?
No, it'll go down.
I just
Yeah,
wanted
so
to
we're
ask
just
if I
wondering-
wanted-
The
But
object wants to
why
keep going
down?
down.
Yeah, well, it
'Cause-
sounds like that if a meteorite falls, right, an asteroid comes in and a meteorite falls, didn't that originally start up? So why doesn't it go back up?
That's a good question.
That so
See, but
it's going down. Any object in the air, especially if you go higher up, is going to be that it's a very low density air fluid up above. And
Yes.
so that air fluid doesn't have the energy level, so it's going to go down to the next level
Well,
and
it's
say,
low
"Oh, I still
pressure.
can't find." What's that?
It's low pressure up the top,
Yeah, and
like
very low
atmospheric
particle
pressure.
density, and
Right.
so it'll keep.
So
If you kept packing air and made it thicker and thicker, eventually
yes,
you'd get to a point where you could sustain something. So if we kept
right,
going down, you would and hypothetically, if the air got dense enough, it would then hit that cushion and float, and it would just float there.
right.
But I mean,
So
that's a theoretical thing because we have not.
what causes that air to be thin up the top, a low pressure up the top, and a higher pressure down the bottom?
So air is a fluid, and just like water, air, gas is a fluid as well. It takes the shape of its container and everything, and spreads its volume out.
Yep.
And so you have fluids, and just like a density tower with all the liquids of your household, detergents and everything, sort out the fluids of the air sort it out as well. So we have these bands of air that are at different densities, and that is actually like if
But
I
it's the
could,
same
can I ask a
air.
question? What's
Yeah,
that?
well, it's the same air. The whole point of a density tower is that they are different liquids of different densities, all
Hmm?
up and down, right? The liquids themselves have like oil has a different.
Oil and water, yeah.
Right. So the oil will go down and
And
the
honey
water
and
will go up.
milk.
Right, but we're talking about the same air, right? There's nothing different between the air particles down the bottom and the air particles up the top, except the ones up the top are more spread out. It's thinner. So why
Well,
is that?
isn't there more like helium and hydrogen up top? There's more water vapor down here than there is higher
Mhm.
up.
Why is that? Why are denser molecules lower than less dense molecules?
Yeah, why don't
Uh,
they mix?
I
Going
think
back to
there's
that
going to be
mass
some like
relation.
excitation. Like if you have heat and water vapor, it's going to different molecules are going to heat up differently. Um, so I think that there are a couple variables that can help kind of keep things cycling, but I think things will find a rest. Like
Do you think
uh,
that air has a resting energy as well? Do you think that air is being pulled down as well and has a resting energy? Do you think it wants to go down as well?
um, so do I think air wants to go down as well? Um, Molecules of gas are they're really high energy. And so like a molecule of gas could go upwards and it can go up pretty high versus like a piece of dirt cannot get that energy to stay up there. So I think molecules can have an energy level and be excited enough to where they go up and they can stay
Okay.
up.
So
Um
molecules, perfect. So which will go further up, a hydrogen or an oxygen molecule?
a hydrogen,
Why is that?
because the energy if you put the same amount of energy into a hydrogen molecule, or we'll say H2 and O2, if you put the same amount of energy into each of those molecules, the O2 is not going to go up as high as the H2 because the H2 has less mass. So if you put more energy into it, it's going to be able to get more out of that energy and go further.
Could it be because you know how we said that the downwards resting force was the amount of mass that it had, right? The more
Hmm.
mass in our ball example, the more downwards force there is, right?
Hmm.
So if there is more mass in a oxygen molecule than there is in a hydrogen molecule, wouldn't that mean there's more force on the oxygen molecule?
That's the kind of the other, like explaining it backwards. Yeah, you
Why?
could you could say the oxygen has more downward, or that the hydrogen has more upward. They're gonna relative to one another. They're gonna be at the same. The oxygen is still gonna be lower than the hydrogen.
But
So
if
I think
this,
I think both of those explanations can explain.
well, I'm just wondering why there has to be an upwards thing at all. because if I've got my ball and a bigger ball, right, and this one has less resting force on it than the bigger ball, why couldn't we just substitute those two things for hydrogen and oxygen?
Can you repeat that one more
So
time?
we've got my small ball, right? And
Mhm.
that has less resting force, as you call it, less downwards, wants to be downwards, than the big ball of the same stuff that's got a lot more mass to it, right? So if we just interchange those for hydrogen and oxygen, sorry, I can't say the big
Yeah.
oxygen one,
Hypothetical ball, big ball.
right? The hypothetical ball, the big ball.
It,
Then
but
you
oxygen
that's
and hydrogen are different.
well, yeah, I'm not
Those
arguing
two
that.
balls are that we were talking about earlier were the same density. Oxygen and hydrogen are different. But just curious, can I ask y'all a question
Yeah,
that
of
I
course, of
am
course.
curious about?
Sorry.
Just because I and thank you for these questions. Because one, I like the thought provoking stimulation and everything. I think it's fun to think about. And I really like these conversations. So thank you all very much for all this time and everything. But I am curious this. So on a globe, we're told about the how we have a gradient of air pressure, and then up at the top it's low density, and then there's a vacuum
Low pressure.
next to this low pressure,
Yep.
and we're actually losing atmosphere escape. We're losing
A
so
tiny
many
bit.
tons of
Yeah.
atmosphere to space because in a vacuum gases want to spread out and homogenize the whole area because gases take
That's
the
not
shape
what
of a
vacuum
container.
means.
What's that?
That's not what vacuum means. Vacuum simply means devoid of matter.
Yeah,
So if you take an area and you make it devoid of matter, you have a vacuum. And that's why the
it's incredibly
vacuum of
low pressure,
space is a
right?
vacuum. Well,
Well,
depends on what you mean. Like matter pressure, yes. Radiation pressure depends. The interstellar medium has a higher radiation pressure than our solar system does. And in fact, there's a place where they meet, and I believe that's called, oh shit, I can't remember what that is. Is that the heliopause? Anyway,
Heliopause, yeah.
yeah. So
Heliopause.
at the end of the day, it's going to depend on what you mean by pressure. But really quickly, there was one other thing I want to say that I wanted to say, and I want to say it before I before I lose it. This will be really quick.
go for it.
Is that you
I'll
said
ask.
that why massive bodies attract essentially is like a philosophical question. That's actually not. Science, physics tells us perfectly clearly why it does that, and those explanations in fact give us predictions, and there actually isn't a single one that this particular theory has ever failed. Not a single one that hasn't come true. Not one. Not ever. Not yet.
Okay.
Okay.
Go, Nathan. Yep.
And so, interesting that you say that because I want like a Van de Graaff generator can flip and cause something to go up, but I know that also has to do with energy levels and exciting
Electricity.
matter.
Yeah.
And
It's electrons.
but okay, so if you took, so gravity is gravity why we have an atmosphere, why our atmosphere is held to the Earth?
Yes.
Okay, so and gravity, the closer to the center of mass, the stronger gravity is.
Ideally speaking, yes.
Okay. And then like you know how like there's strong and weak vacuums, right? Like some vacuums can be stronger than others.
I don't like maybe Hoover vacuums, yeah, but not physics vacuums.
Okay. Like if you took like a cup of they say like if you had a cup of water, put like a coaster on it, turned it over, that vacuum at the top is not as strong as like a machine made vacuum.
That's not
Um
a vacuum at all. Well, so you're saying about the force holding that thing onto it, kind of thing. Is that what you're saying? Holding the coaster onto the glass. That's what you're talking
He's
about.
talking about vacuum pressure, the pressure differential that holds the paper, but it's not like there's a vacuum in there. It is a pressure differential with respect to the density of the atmosphere that holds the paper there.
And so some can be stronger and weaker pressure vacuums.
Well, they're just
So
closer to a
pressure is a gradient.
They're closer to a perfect vacuum or further away from a perfect vacuum. But if you were to describe it like that, you could describe our atmosphere as a really, really weak vacuum, and that would be a really inaccurate way to describe it.
Gotcha. Okay.
Yeah,
Um,
like for instance, in my lab, I've got vacuum chambers that I use. I got to suck all the air out. Got a tube that's attached to it. Turn the spigot, close it off, and now I've got a vacuum. That's what I would call a vacuum.
Mhm.
It's a space that it has very, very low pressure.
But it's not a
And-
perfect vacuum because
Not a
So-
perfect vacuum, no,
Yeah.
definitely. But
But
it's
it's
better.
strong.
It's at least enough to get the bubbles out of the medium that I need to get it out of.
Yeah. Okay. And this vacuum, just like there's a barrier. It's in a chamber, right? A vacuum
It's in a chamber. Yep.
So if you took a vacuum, gravity is what holds our atmosphere to prevent complete blowout and escape of all of our atmosphere into space. So we have this gravity, and it's stronger the closer to the earth that we go. So if you were on the surface of the earth and you had in a chamber, in this chamber there was a box, and there was air molecules in that box, and you had this box sealed, and then surrounding that was this vacuum chamber, and you suck out all the air and make a strong vacuum. Now you have essentially a weaker vacuum, I think, in terms of torr than outer space would be compared to this pressure. And then this box is also closer to the center of mass, so it's got a stronger gravity holding it down. The gas molecules in that box that's still sealed up. If you open that box, are the gas molecules in that box going to disperse throughout the vacuum, or will they remain in that box?
They will disperse.
All within this vacuum chamber.
They will disperse.
Is what?
They will disperse. They will
They
equalize.
will disperse.
Yeah.
Okay. They will disperse. So, So then why can gravity not contain the gases within that box and prevent them from dispersing, but can prevent
Yeah, so you're asking why our atmosphere doesn't do the same thing. So you were sort of describing a resting energy, right? And we sort of agreed that the more massive our ball is, the more mass our ball is, the greater amount of resting energy it has, right?
Mhm.
Right? So if we inflated this ball to the mass of the Earth, not just the density, but to the mass of the Earth, how big do you think the resting energy force would be then?
well, the Earth has a large energy, but aren't the gas molecules aren't at rest.
Yeah, I'm not saying that. But so for some reason you think that this matter that gets resting energy, that gets pulled down, but gas molecules which have mass, they have what? Oxygen's what? Oh god, 8, is it 8 protons? Please, someone help me. I'm terrible at chemistry.
Yeah, it's like 8 grams per mole.
Yes.
Right. They don't get resting energy for some reason. Why is that?
Well, I'm just like and I'm sure if you had like a gas like an oxygen molecule stop, if you could stop an oxygen molecule, it would have a resting energy. And so I might have misspoken there.
That's okay. Okay. Well, they have the resting energy as well. But so the thing you've got to remember about a vacuum is a vacuum doesn't suck, right? It's kind of this joke that vacuums don't suck, pressure blows. The pressure is actually pushing out into the vacuum. It's not actually being sucked away, kind of thing. The counterbalance of that atmosphere is the resting energy, if you will, of those oxygen molecules. So the resting energy from them, they get pulled down, and because they're very low pressure, or very not dense, basically, they can all squeeze into a place. But when you squeeze stuff into a place, when you compress it, it wants to fling back up, right? It wants to expand again. So basically, that resting energy of the air molecules is all squeezed up, and basically that's why it becomes less and less dense as it goes up, because it's being squeezed, and then some can rise up, and some can rise up, and some can rise up until it's very far away from the Earth. So it's the resting energy of the air molecules that is keeping those molecules against the Earth.
Okay. So if you took this this box in this vacuum chamber and it was maybe like a foot tall or something and had some helium, hydrogen in it, some oxygen, nitrogen, would
Well,
this box form a gradient, or would all of the molecules disperse?
Well, the question is, would the gradient be detectable, kind of thing? It would be very, very, very slight gradient at that amount. But I guess my point is that the way that this resting force works, which we're just calling gravity, I'm just replacing one term for another. In order to do that to air in a vacuum chamber, you would need a box the size of the Earth in order to generate that amount of resting energy to pull on it.
Gotcha. So it's one of kind of one of those things where you'd have to have
You would have to have,
something Earth size, planetary
Earth-sized, right?
size to be able to show
Right.
the example. Okay.
Yes.
And like
Or
so
not Earth size, Earth mass, to be really, really specific, because it could be something small and be insanely massive, kind of thing.
like a neutron star or some white
Right,
dwarf should
right,
be able to-
exactly. So you would need, it could be tiny, just the mass has to be there.
Okay. So
Can I add a quick caveat?
yeah,
Sure. Just make me look
So
silly. Go for it.
just because I think it's an interesting point, and it's one I think I've seen doesn't really get mentioned a lot in these kinds of discussions, these flat Earth discussions, is that when you're talking about if you had a gas in a box, would there be a differential from the bottom of the box to the top of the box as a result of gravity? Probably yes, maybe. But there's no way we're ever going to detect it, because the thermal pressure in the box as a result of the thermodynamics of the gas is going to overcome that, and the gas will distribute until it sits at thermal equilibrium. And there are similar thermodynamic processes happening with the atmosphere as well that play a role in the structure of our atmosphere. And that's a thing that we have to remember. So, I mean, not that anything that Mark is saying is incorrect. It's not everything he said was right.
Oh, that's
with gravity and everything like that.
there are multiple variables that factor into.
But yes,
what we,
thermodynamics is a very important part of this. Yes,
exactly. Yeah, with the density of air, it is just so low that you have these other forces that now come into play that end up dispersing whatever gradient might be generated from the effects of gravity. Now, one place where you don't see that, getting back to the pool example, is in a pool. You dive down to a deep pool, you go down 15 feet, you can feel that pressure on your ears because there's a little bit more pressure.
It's a lot more, greater pressure. You have all the water
and
above you.
Of course,
it's a lot more for the
much
thermodynamics to push
absolutely
on the water.
The thermodynamics of that is not going to be dispersing the water very much.
And now, hypothetically, if you were able to cool these gases down to a very low, say near 0 Kelvin temperature, then you would have a more likely chance of having a gradient hold for a longer position or a longer period of time, because the heat is not there to create.
Oh yeah, most of these elements, once you get down to 0 Kelvin, would be in solid state. I think almost every element will hit a solid state before or at 0 Kelvin. I think I want to say that there's an objection, but then that there's also nuance to that objection. So I'd have to go look at it again. But
yeah, I mean, like near 0 would be
every element.
because at absolute 0, there's no motion, no particle motion.
It's essentially quantum mechanical thermal equilibrium. Yeah.
So, all right. Well, I'm going to bow out, guys. It was great to talk to you, but I'm going to bow out. So, thank you so much. And Nathan, it was great to talk to you, mate. Really. See you, and have a good day.